So I'd like to quickly link back something we learned earlier in the course with what we're learning now is hierarchical modeling and animation. They go together really well. And if you do it appropriately, if you do it right, hierarchical modeling supports animation. Hierarchical modeling, if it's done correctly, enables you to simplify your modeling, your animation problem, and by using local animations. So just like with hierarchical modeling, you can solve this local problem of rotation and transformation, we can do the same with animation. We just solve a local animation without worrying about the bigger picture. So it works in the same way. Okay, so for example, let's say I have a program that has a bicycle and I have wheels on the bike, which go round and round. If I want to make those wheels turn with hierarchical modeling, I just modify that rotation matrix inside that, when I'm drawing a wheel, modify the rotation matrix. Forget about the rest of the bike. If I want the whole bike to tilt, I'm doing a wheelie, I just put a rotation matrix in front of the whole thing and everything turns. And what if the wheels are turning at the same time as the whole bike? It doesn't matter. We've solved that with divide and conquer with hierarchical modeling. So let's look at demo 15. All right, so demo 15. So this is a program. We have a bike that we're drawing. The draw looks like this. We draw a background, which is nice. We draw the road, push matrix, pop matrix to make some road. Then we position a bike. We have push matrix. We translate scalar bike, and we draw it. We have this wheelie here. This is a wheelie T. So I'll start a wheelie, which is where you pull the front wheel up and use its own T to keep track of the lifetime and how long it should last. If it's currently in the middle of a wheelie, we add an additional translate. We rotate it basically, but we use the trick we showed earlier in the class. We translate to the center of where we want the rotation to happen, the bottom left corner. We rotate and we translate back. Cool. If not, we don't do the wheelie. So this is the first example of solving a local problem. I don't care how you're drawing the bike. It's right there. I just modify U before I go in. I go, okay, translate, rotate, translate, then draw the bike. And I can get this wheelie effect, okay? And then I put some trees. I update my time step. T plus equals, I move along. And then as it goes to the end of my T, I go back. So it just cycles. I update my wheelie T. I wouldn't worry about it. So when I'm drawing the bike here, we use hierarchical modeling. First a rear wheel, but we draw the rear wheel by positioning it, rotating it, and filling it and drawing it. But look at this here. The rotation depends on the T. Okay? So as my T changes, that rotation will change. I can modify the rotation of that wheel locally. I've pushed the matrix, popped the matrix. I don't worry about everybody else. The front wheel, same thing. I have that multiplied by T. Cool. And then I draw my frame, the bar. I draw the bars for the frame. I draw the all the pieces. I have a unit tree that I'm drawing as well. Don't worry about it. The only other thing I'll mention is that the wheel function itself doesn't handle a rotation, right? We draw a wheel, and if you want to position me or transform me, you do it before you call me. Hierarchical modeling is great. I also have this feature where we draw an outline so you can see the local coordinate system of all the pieces we're drawing, and that's actually kind of fun. So here's my hierarchical model example of animation. Look at that. So you have a bike that's moving from left to right as T goes from 0 to 1, and the wheels are rotating from that. Now I can click, which does a wheelie, and you see what's cool is it does a wheelie independent. The wheels keep rotating, everything else keeps moving. You can solve that local animation problem without worrying about everything else. It's also kind of fun to see the, especially if you zoom in here, it's kind of fun to see all the little boxes of the local coordinate systems. So download this demo and play with it. All right. So that's the first thing we'll talk about. Animation fits, wanted to talk about, is that animation fits really well into hierarchical modeling. However, I want to talk a little bit more, a little bit about something else. There's another technique we can use to combine hierarchical modeling and animation to simplify our problem. So we basically use what's called a skeleton model. So to simplify animation, we define a skeleton. Okay, we define a skeleton as a kind of like this. So you can imagine I have a human like that, and there's another joint there, there's another joint there. So we define this skeleton, and you can see now I have a person. And what we do is, this is a simplification of a complex object. This could be a really complicated character with a lot of models, a lot of polygons, but we have this simplification here. Okay, this problem of creating a skeleton to fit the object, this has a special keyword. It's called rigging. We come up with this model, we attach it to our object. This is called rigging. And then the next part of the problem, once we have the model, the skeleton rather, that fits our model, then we attach all of our complex geometry to the skeleton. And by attach, I just mean drawing that local coordinate space, be in the space of that bone or that segment, okay? So we attach to this skeleton. So you can imagine we come along here and we put all these geometry pieces along the skeleton to get our shape, you know, maybe some body armor, big beefy pants, right? You can imagine doing something like this, right? This is called skinning. Okay, so this is another keyword. This is called skinning. Once we do that, all we have to do is we animate the simple skeleton, which makes our problem a lot easier. A lot easier than trying to manage all these micro small pieces. So when we do this skeleton, we can actually improve our realism by involving rules and limitations, okay? Oops. So to improve realism, and it also helps to simplify the animation. You'll see why. We can impose rules and expectations on the skeleton, and these will depend on what the skeleton represents. A car will be different than a person, will be different than a dog. Okay, so for example, we cannot allow the elbow to move backward. Right? We can't allow it to move backward. It doesn't make any sense. Just don't allow that to happen, etc. These kind of things. So you can take this idea of imposing rules, imposing realism on the object, and you can actually combine this with the physics that we've been talking about above here, and we get what's called ragdoll physics. Now, all that ragdoll physics is you impose a physics model on the skeleton. So we do physics, so collisions, motion, that kind of thing. Collision detection on the skeleton. And then you can, ragdoll traditionally treats it as a limp doll. So there's no muscle, person's not pushing, nothing's happening, just suddenly you go limp. And so you'll see this in video games where suddenly the person dies and they go limp. It's a ragdoll physics. So we take the skeleton, we apply physics to it because it's too complex to do physics in the whole thing. We just do it on the skeleton and we get this really nice effect. We can also use the skeleton to define keyframes, right? So you can imagine taking your skeleton, positioning it, click keyframe, position, click keyframe, then interpolate. Okay? So the skeleton simplification really gives us a lot of cool options of what we can do. Okay, so I'm going to jump over to our slides. Where are we? Ta-da! We saw that. Cool. So here's an example. I won't show the whole thing. Thanks. I'm not sure all these controls are for. Come on. There we go. So here's a skeleton-based animation. And I like this video because, I'm not going to show the whole 13 minutes, of course. I like it because it shows, first of all, oh, I missed it. Missed what I wanted to show. It shows the skeleton inside. So they've shown the skeleton inside, they've rendered it nicely, and then they show you your code. Of course, nobody cares. But what's really neat about this is they skin everything on top of the skeleton and just modify the skeleton. This enables you to do really cool things with animation. They can put like textures and things on it. But yeah, look at the skeleton underneath moving and everything else is just attached to it. You can create keyframes. You can interpolate. They actually had an example of that. Keyframe, click, save. Keyframe, click, save, and ask it to interpolate using the kinds of things we've learned. And then you get a very smooth looking motion and you can modify the keyframes to change. There we go. See, interpolating. Yay. So skeleton models are really powerful. They're a really nice way to simplify your modeling problem. I also wanted to show this. Oops. I also wanted to show this. And warning, this might look a little bit gross to some people. If you're nervous about seeing human-like things get hurt, maybe skip this part of the video. I find it painful and I'm not sensitive. So here's a game showing ragdoll physics. So you have this character, actually, yeah. And you see what it's doing is it's doing physics simulation on the body. Poor thing. And then using this terrain to play with it and to try out the physics. Cool. So you can do ragdoll simulation. This whole video is bad things happening to this poor model. That's the whole video. Like, let's push him off. There we go. Right? And so, yeah, ragdoll physics. You can do that with your skeleton. So back to our slides. The last thing I want to talk about with skeletoning and this idea of using putting your skeleton underneath your model is the idea of what we call forward and reverse kinematics. These are keywords. We don't really learn this in this class, okay? It's beyond this class, but I want you to know what the keywords are because it's going to come up in the real world. So forward kinematics is this idea of, if we transform our skeleton if we transform our skeleton along all the joints, ... where are the endpoints in the real world? Where are the endpoints? So I'll give a simple example here instead of the human skeleton. If I have this actuator and it's moving here and you transform and you translate in 3D and you come down here, where is that? That's called a problem of forward kinematics. It turns out that we already know how to solve this. We can solve this using our existing linear algebra. So you've already solved this. In fact, this is exactly how the graphics pipeline works. This is exactly how the graphics pipeline works. So basically, if we have our transforms of these matrices, we multiply them together, we multiply them by the point, bam, we can calculate that. So it turns out this is really easy to do. If you've taken graphics, it's easy to do, not a big deal. The reverse problem is called inverse kinematics. Now, inverse kinematics is working in the opposite direction. And that is, if we want the end effector, the end point, to move in a specific fashion. It's very specific. So if I go back to my other example here, if I have something like this, now if I want this endpoint to move this way, what do I do? Now the simple solution is I'll just move that joint, but it's not always possible. We can also move that point. I can also move that point. Maybe I can also move that point. So there are multiple solutions, and it's not always best which one that we should be using. So there's many solutions. Okay, with some better than others. You can get stuck, you can get caught. This is actually a really hard problem, and we're not going to get into it in this course, but you should be aware that when people talk about inverse kinematics, it's tough, it's challenging, it's commonly used in robotics, but very also commonly used in graphics. So I'm going to quickly show a video. And this is a inverse kinematics video, apparently someone's using Unity, but I want to show you a few things here. You see that part there? The person's hand hits a ball, the hand moves back. That's inverse kinematics because you want the hand to move exactly where the ball is, and the rest of the arm should move nicely to match that. Okay, that's an inverse kinematics problem. Here we go. So this is inverse kinematics. You're moving the endpoint, and you see how it jumped there? There's multiple solutions. Yeah, see? That's not cool. You can't do that with real robots, and you shouldn't be doing that. But that's an inverse kinematics problem. I move the endpoint, and let's see what happens. And this is a really cool video about how this person's doing it in Unity. Okay. All right. That's basically all I have to say about animation. So if you have any questions, come by and ask in the forums. Thanks.